So we've talked about the oceans and, kind of the importance of oceans in terms of Earth systems. We're going to focus in on water right now and talk about the availability of water, where it is, how we use it as humans, and what we can do to conserve it. 70% of the Earth's surface is water. So the majority of the Earth's surface is water. Of that 70% water, 97.2 is salt water that's contained in the oceans. So almost all of our 70% of water is salt water. Fresh water is only 2.78 of the Earth's water. Obviously, that's 97.2, the difference between 97.2 and 100. Fresh water is found in the following reservoirs: ice and glaciers, underground reservoirs, bodies of surface water like lakes, rivers, streams, those kinds of things, wetlands, and then atmospheric water. And what I have done here is put the percentages next to each one of those. And as y'all can see, the biggest percentage by far is ice and glaciers. Fresh water is primarily found in ice and glaciers. By the way, that's a test question almost every year. They're looking for you to know the percentages and where those freshwater reservoirs are. Frozen water in ice and glaciers is technically inaccessible to humans. While we could theoretically go and hack off a chunk of glacier, melt it, and have fresh water, that's not really a very practical solution to getting fresh water. So we actually say that only 1% of our freshwater resources can actually be used. And those are these two right here: underground reservoirs and surface bodies of water. That is basically where humans get their fresh water from. We pump it from up out of the ground, and we use it from freshwater surface reserves. So underground water, let's talk about water that exists underground first. Underground water exists in permeable layers of rock and sediment called aquifers. So there are two types of aquifers. The first type is the unconfined aquifer, and it's what you probably would imagine. It does not have confinement, so the water flows easily from underground to the surface. The second type is called a confined aquifer, and a confined aquifer is surrounded by an impermeable layer of rock and clay. A confined aquifer cannot actually flow to the surface, and oftentimes the water in a confined aquifer is under quite a bit of pressure. The water table is the uppermost level at which groundwater saturates the soil. So if you dig down through your soil horizons, which you guys have already learned about, eventually you will hit water. And what that is, that's the water table, that uppermost level where groundwater is saturating the soil. And in different soil types and in different ecological areas, the water table is either higher or lower to the surface. Groundwater can be recharged when precipitation percolates through the soil layers and flows back into these unconfined aquifers. A confined aquifer, however, can only be replenished if there is access through the impermeable layer that surrounds it. So here's the deal. When it rains, the water percolates down through the soil and can recharge the unconfined aquifers in the ground. But confined aquifers, they cannot be recharged quickly, easily, and sometimes not at all, depending upon how confined they are. So when we actually dig down and we tap an unconfined aquifer, and we do that oftentimes to get at groundwater, we know the water's down there. When we do that, once that confined aquifer is tapped, if you use all the water out of it, it's very difficult to replenish it. Even though there's now a hole in it, it's still largely capped by this impermeable layer. Water from some aquifers naturally percolates to the surface in a seep called a spring. You've probably heard, different bottled waters say this is spring water. Well, spring water is just groundwater. It's water that comes up from the ground. It's fresh water. And springs can have a number of different qualities depending on the rock that they're surrounded by. They have different mineral contents. Springs are considered a freshwater aquatic biome, and many have been used for centuries as important sources of fresh water and as gathering places by humans. Actually, if you want to know an interesting story, the city of Dallas actually had many springs that were present all throughout the city. One of the largest areas of springs was where Old City Park currently is. If you go in towards downtown, you may have actually visited there. On the left-hand side of I-30 is an area called Old City Park. And there's some naturally occurring freshwater springs there that Native Americans gathered by and used for thousands of years. Well, when the white settlers came to Dallas, they did not like the fact that the Native Americans were gathering at these springs. So they purposefully plugged and diverted the springs so that the Native Americans would not gather there and would not have a source of fresh water, which was not a very nice thing to do. So aquifers that do not naturally reach the surface can be tapped by digging a well. So modern water wells are very deep, and water is pumped out of them against gravity. So you put down a pipe down there and water is basically sucked up. It's pumped up. In some confined aquifers, the water is under pressure, and I actually mentioned this before. So tapping into the confined aquifers allows the water to burst out of confinement and rise to the surface without a pump. This is called an artesian well. This was actually something that early settlers did quite a bit. They knew that there was water in an area, and they would dig down and puncture these confined aquifers. Then they would have a source of naturally flowing fresh water, because they did not have the technology to have it pump against gravity. The age of water in the ground and its recharge rate varies widely. Water in an unconfined aquifer recharges pretty quickly because basically it's just rainwater that percolates down. Due to this, unconfined aquifers are much more likely to be contaminated or polluted with chemicals from human activity. All right, so think about that. You were talking about water that's in the ground. If it's coming down, if it's percolating down from rainwater, anything that's in the soil or any atmospheric pollution percolates down through and gets into the groundwater. Now, soil, the water movement through the soil does actually remove quite a bit of pollutants, but if the ground is polluted, then we have movement of pollution and chemicals from the soil into the groundwater. Confined aquifers are recharged extremely slowly, as I had mentioned before, like 10,000 to 20,000 years it takes for a confined aquifer to recharge. It's a long time. So large-scale water withdrawals from an unconfined aquifer are unsustainable. The water just can't be replenished in a reasonable amount of time. Even though we've punctured the confined aquifer, that doesn't mean that that it's recharging very quickly, because again, most of it would be covered by an impermeable layer. So here's a test question, always. If you haven't heard of this place before, the Ogallala Aquifer. The Ogallala Aquifer is the largest aquifer in the United States. It underlies parts of 8 different U.S. states, including Texas, New Mexico, Oklahoma, Kansas, Colorado, Nebraska, Wyoming, and South Dakota. There is a picture in your textbook, and you're going to see a picture in the slideshow as well. The water from the Ogallala is used primarily for agriculture, but it is also used for residential and industrial use, and that includes fracking. The southern Ogallala water is usually purchased through a subcontractor for fracking purposes. Most of the Ogallala recharges very, very slowly, but the rate of water withdrawal by humans is quite quick. Scientists think that the aquifer could be depleted by mid-century, so we're talking like 2050. Rapid pumping of, so we're moving away from the Ogallala. I'm going to show you a picture of the Ogallala here in just a second. Rapid pumping of a deep well can cause adjacent shallower wells to go dry. This is known as a cone of depression. I'm going to show you a picture of what that is because it's kind of hard to picture without seeing it in a diagram. Okay. All right, so here, as promised, is a map of the Ogallala Aquifer. Now remember, this is underground. What you're seeing there is ground penetrating radar pictures, so they can tell you how deep the water currently is. And this is obviously the southern end of the Ogallala, and this is the northern end. Water levels in the northern part of the Ogallala Aquifer are actually pretty stable, especially in this area up here. And that is because there is not a lot of humans doing stuff in that area. Not a lot going on in terms of water withdrawals. But down here in Texas, New Mexico, and Oklahoma, and it's like right in this area right here, this is a prime agricultural area. And the Ogallala is used, again, primarily for agriculture. So they're pumping it dry. Again, scientists are estimating the depletion at least of the southern end by 2050. And nobody really knows kind of what's going to go on after that. How is agriculture going to get its water? We really don't know. It's not a problem that, I mean, people are aware of it, but there's not a plan in place to mitigate what's going to happen when it does run dry. All right, so here is the slide that talks about cones of depression. And so what we were talking about is when deep wells are pumped quickly. So right here you can see, oops, I keep moving that. Try that again. All right, so here is a deep well, deep water well. Here is a deep water well. Here is a shallow water well. All right, so when these deep water wells puncture down into the zone of saturation, into the groundwater, and rapidly suck water up from out of the ground, it creates these cones of depression. And that's what you're seeing right here, where basically the water around the well, the groundwater on the well, is depressed from what would be the water table right here. And there's the word water table. Okay. And so the shallow well, which previously reached the water table, can no longer do so. This is actually a little bit of a social justice issue because normally the shallow wells are older and they're owned by people who dug them a long time ago. So we have these big water companies that come in and they drill these really deep wells way, way, way down into the zone of saturation, way down into the water table, and rapidly pump the water out. And so people who had maybe drilled these shallower wells, farmers and ranchers that were kind of first to the area, no longer have access to water because even though they've got a well there, the water table has dropped so quickly around these cones of depression that their well no longer reaches the groundwater. All right, saltwater intrusion into freshwater wells is a problem along coastlines. So I want you to think about where the land meets the ocean. Groundwater near the coast exerts a downward pressure that keeps the ocean from flowing into freshwater aquifers. So you've got fresh water that's underneath the ground, right, in saturating the soil, and it's exerting a downward pressure so that the ocean water cannot flow into these aquifers. But when the groundwater is withdrawn from the aquifers, especially if it's withdrawn rapidly at a rate where the percolation can't recharge it, the adjacent ocean water rushes in to that empty space and it makes freshwater wells salty. Once freshwater wells are salty, once they're salinated, they can't be unsalinated. So basically it means that well is useless unless you go through a desalination process once the water comes to the surface, which is really expensive. Land subsidence and sinkholes are additional issues when groundwater is pumped quickly. So subsidence can occur for many reasons. And if you actually Google subsidence, there's subsidence, only one cause of subsidence is groundwater removal. But since we're talking about groundwater removal, we need to talk about subsidence due to that. So it's a downward shift of the land that occurs when a void is created in the underlying soil structure. Again, when you pump out groundwater very rapidly, you get a void or a vacant space, and the soil settles down into that vacant space. That's subsidence. Now, sinkholes are a very large and rapid type of subsidence. So sinkholes are formed in particular soils, especially where you have subsurface limestone. This is a major problem in parts of Florida. Florida is honeycombed underneath the soil with very, very porous rock in limestone formations. And that rock lies like a sponge. It contains a lot of fresh groundwater. Well, when you pump the fresh groundwater out of those porous structures, there's no longer hydraulic support that keeps the structure, that allows the structure to have to not have air spaces. So as soon as that air is there, all of that limestone then collapses, kind of like a house of cards, and you end up with large sinkholes. I'm going to show you a picture of that here in just a sec. Okay, so here is a famous picture of the San Joaquin Valley. This is in California, and you can Google this. The San Joaquin Valley is a very, very high output agricultural area of California. They started pumping the groundwater for agricultural use around 1900, a little after that. This picture was taken in 1977. See that right there? 1977. I want you to look at the pole. This is the dude down here, San Joaquin Valley. He's standing at the ground level. The ground level was right there in 1925. The ground had subsided to this level by 1955. And in 1977, it was where this gentleman is currently standing. That is a massive amount of land subsidence. And the reason that we use this picture a lot is because San Joaquin Valley is a pretty dramatic example of what can happen when you pump out groundwater. Now, it's happened over a number of years, right? And it's happened slowly, so it's not like, people are like having immediate things falling down into the earth or anything like that. But this is what happens when you pump the water out of the ground. The land kind of compresses and collapses, and you get a subsidence of where the ground actually used to be. All right, so here is a sinkhole. Again, sinkholes and subsidence, part of the same kind of phenomenon. This is a recent sinkhole that occurred in Florida. It swallowed a home and the home's swimming pool. Florida is particularly prone to sinkholes because it has extensive subsurface limestone formations. Again, those are very, very fragile, and the groundwater is what keeps them intact. So as soon as you pump the groundwater out, those things kind of collapse, again, kind of like a house of cards. The formations lose the hydraulic support. There have been many cases where homeowners are actually killed when their houses fall into a sinkhole. You can see it would be pretty obvious if you were sleeping in the middle of the night and all of a sudden your house fell into a hole. You have the potential for quite a bit of injury there. And frankly, if I was this dude right here, I might be moving. But yeah, this one's and this is actually a fairly small one. Sometimes they're very, very, very large. Florida leads the nation in sinkholes. Guess who's number 2? Texas. Yay, we're number 2. Number 2 in the nation for sinkholes. Yay. Okay, so surface water. Now, again, underground water, we can reach it. We use it. Humans use underground water for agricultural, residential, and industrial purposes. Here's the other way that we get our water, and that's surface water, water that's flowing right by us all the time. Surface water is the water that exists above ground in streams, rivers, ponds, lakes, and wetlands. Okay, world's 3 longest rivers by volume. Be very careful. If the test asks you by volume or by length, these answers are different. So the 3 longest rivers by volume are the Amazon, which is hopefully located in South America, the Congo, which is in Africa, and the Yangtze, which is in China. And that is how you say that in Chinese, by the way, not Yangtze, which is how Americans say it, but the Yangtze. Early human civilizations were centered on rivers because rivers provide a means of transporting goods easily. Rivers provide a source of easily accessible fresh water. And the seasonal flooding of rivers enriched the soil on floodplains and helped make agriculture more productive. And these are all reasons that you probably learned in AP Human Geography or World Geography if you didn't take a PUG. Okay, atmospheric water. Atmospheric water is a reservoir of water. It's not really accessible to humans. It's not like we can go up there and grab water out of the clouds easily. But as you can imagine, atmospheric water is really, really important to global water distribution because atmospheric water is the way that we get precipitation. So most countries that practice subsistence agriculture, that would be countries that are developing and do not have industrial agricultural complexes like the U.S. does, rely solely on precipitation for the success of their crops and the survival of their livestock, which means that if a drought happens, right, that they're in big trouble. A drought's a prolonged period of little or no precipitation. Droughts just don't affect the survival of crops and livestock, however. Droughts affect nutrient cycling. We're going to talk about biogeochemical cycles here in the next few weeks. So when we're talking about the carbon cycle and the nitrogen cycle and the phosphorus cycle and all the other earth cycles that we're going to talk about, when we're in extremely dry conditions, those cycles are very, very much affected and sometimes break down. Droughts also increase topsoil loss. And this, you guys learned about this when you learned about the Dust Bowl. So when the topsoil is subject to a drought, when it dries out, it blows away more easily. So when you've got the wind coming across a place that's very dry, it takes that drought affected topsoil with it. This is what happened in the middle part of our country. We had a couple of different things going on during the Dust Bowl. We were in the middle of about an 11-year drought, and the farmers in that area were practicing a deep till agriculture that tilled very, very deeply into the soil horizons and made a lot of that topsoil come to the surface where it was oxidized and dried out and then blew away. So the Dust Bowl had several components of its cause, but drought was a major component in terms of topsoil, both drying out and loss. So when rain finally does arrive to break the drought, the ground is often too hard to absorb it, and the rain, instead of percolating down like it should, you get sheet and gully erosion, which we talked about when we talked about soil characteristics. You get sheet erosion because the ground can literally not absorb the water, and you get soil erosion. So if your topsoil is already damaged from this prolonged drought, rain comes and you're like, yay, rain, but the rain actually can't soak in, and all the rest of your topsoil goes washing off into your rivers in a soil erosion event. Flooding occurs when water input to an area exceeds the ability of the soil to absorb that water. Flooding can happen in soils that are damaged by drought, but it can also happen when just a lot of rain falls in a short amount of time. Human activities can worsen the risk of flooding. Humans pave over soil and we erect buildings. When we do that, the soil is no longer permeable. Buildings and pavement create impermeable surfaces. Rainwater, instead of percolating down there, runs off the surfaces into storm sewers or local streams, which means it doesn't have the chance to percolate down into the soil and to recharge groundwater reserves. This excess runoff also overfills local streams and rivers, which can overflow their banks and flood adjacent areas. So the greater the amount of impermeable surfaces, the lesser amount of groundwater groundwater reserve recharge, and the greater amount of runoff events and flooding. Human alteration of water availability. Most rivers are subject to periodic floods. That's kind of what rivers do. While flooding can actually bring nutrients to a floodplain and assist with agriculture, it can also disrupt human activity. It can kill people and it can destroy property. So we do a lot of things to try to mitigate or prevent flooding. One of those things is we build levees. A levee is an enlarged earthen bank on each side of a river, and it's designed to contain floodwaters. The Mississippi River, why do I always do that? Silly me. The Mississippi River has the world's largest system of levees. The Mississippi is actually levied pretty much the whole way down. All right, so let's talk about levees, and I'm going to show you a picture if you can't kind of visualize what they look like. Levees have several drawbacks. Well, number one, they reduce floodplain fertility because you no longer have seasonal flooding on that floodplain area. Number two, the sediments that naturally flow down a river cannot leave the river and settle in the floodplains during this normal seasonal flooding. So the sediments are carried further and further downstream, and they eventually deposit in the alluvial plain of the river, which leads to increased sedimentation where the river enters the ocean. A lot of rivers, where they enter the ocean, that area has to be dredged every few years because so much of the sediment that would normally be deposited in the floodplains now reaches the alluvial plain where it actually enters the ocean. And while levees prevent flooding in certain areas, they force the floodwaters, the excess water floodwater further downstream where it can lead to actually more devastating floods. So rather than the flooding occurring kind of a little bit here and there all along the river, those floodwaters are pushed further down the river where you end up with a gigantic flood, which is kind of what happens with New Orleans all the time. New Orleans is close to where the Mississippi enters the ocean, and so all the floodwaters from the states the Mississippi flows through get contained by the levees, and they all hit poor old New Orleans. The final thing is that levees give people a false sense of security about building their homes in flood-prone areas. Levees can and do collapse, and they collapse with fairly regular frequency. If you think about Hurricane Katrina caused a storm surge in the city of New Orleans, and several of the levees there collapsed, and floodwaters flooded into the lower Ninth Ward in particular of New Orleans. So when they do collapse, you can have severe flooding and a large loss of property and human life, and that's what we did see when that storm surge broke the levees during Hurricane Katrina in New Orleans. Okay, dikes. Dikes are similar to levees, except they're built to keep ocean water from flooding into the land rather than to keep rivers from flooding into the land. So dikes are common in Northern Europe. Most of the farmland in Northern Europe is below sea level. Prior to the building of dikes to keep the oceans out of that area, those areas were flooded. You guys probably, if I say the Netherlands or I say Holland, you might have a picture of a windmill. The reason that there are windmills all along the coast of Holland is because those windmills actually run pumps. They're running pumps to keep the water out of an area. So what they did in Holland, what they did in the Netherlands, is they put dikes up to keep the ocean water back, and then they used wind power. They used those windmills to run pumps that pumped the seawater that did get over back into the sea. And they still do that today. That is still, now a lot of times the pumps are electric, but some are still run with wind power. That is why the coast of the Netherlands is associated with windmills. Those windmills were driving pumps that kept the ocean from flooding that farmland that's below sea level. All right, a dam is a barrier that runs across a river to control the flow of water. Most of you are probably familiar with the concept of a dam. The body of water that's created behind the dam is called a reservoir. The largest reservoir system in the United States is along the Missouri River. The Missouri River is a tributary of the Mississippi. And there are 6 large reservoirs on this river system. They're in Montana, North Dakota, South Dakota, and Nebraska. This reservoir system along the Missouri stores almost 24 trillion gallons of fresh water. Dams can be built for many reasons. Some of those reasons include providing humans with hydroelectricity, flood control. So when we have a river that is flooding and is causing property damage or loss of life, a lot of times they'll build a dam on that river. And then when the river flows, it overflows into the reservoir and makes the reservoir bigger. And then we can choose how much water to let out down the other side. Sometimes we need water for domestic use. So we impound the creation of a dam with a creation of a reservoir behind it is called water impoundment. And we will impound that water so that we can use it domestically for a growing human population. And sometimes we just do it for recreation. People like lakes, and more people can use the lake than they can a river. And so we impound water for recreational use. By the way, this water impoundment for domestic use is actually quite important in Mesquite because Mesquite gets their water from Lake Ray Hubbard. And that was a impoundment that was specifically done to grow the areas in Mesquite, Rockwall, and Rowlett. There was Hubbard Creek that ran through that area, and early settlers used Hubbard Creek as a source of water, but it was a creek. So they impounded Hubbard Creek in order to create Lake Ray Hubbard, and you ended up with the loveliness that is the lake there, and we use that for water for domestic use and for recreation. Dams, especially large hydroelectric dams, provide many benefits to humans, but they do come with financial, societal, and environmental costs. We're going to talk a little bit about the hydroelectric dam pros and cons now, but we're going to really delve into that when we start talking about alternative energy and renewable energy. So this is kind of just like dam overview. So fossil fuels during dam construction is a big deal. It's a negative. Dams also change species composition in an area, and there's usually a loss of both aquatic and terrestrial biodiversity. You're flooding the entire terrestrial ecosystem when you create a reservoir, and you're drastically changing the downstream ecosystem of that river. So you have aquatic and terrestrial species composition differences, and generally speaking, a loss of biodiversity. You have displacement and disruption of human communities. Now, in the US, we're largely not building any new hydroelectric dams, but the same is not true for many developing nations. China is still building hydroelectric dams, as is Brazil. And for instance, when China built the Three Gorges Dam, hundreds of communities that were upstream in the reservoir area had to be relocated because their villages were flooded. Also, dams disrupt fish migration routes and increase fish mortality. Well, how do they increase fish mortality? Well, hydroelectric dams have turbines that the water flows through in order to generate the electricity. When fish pass through those turbines, they get chopped into little fish bits. And so there are a number of different strategies to help the fish kind of deflect from going through the water intakes that would go through the turbines. But the fact is that when you have fish and hydroelectric dams, there's increased fish morbidity or mortality because they get chopped up by the turbines. We also have increased methane and carbon dioxide emissions from the reservoir water due to increased rates of decomposition. There is decomposition in the water in rivers. However, when you slow down water, it gets warmer. When water gets warmer, rates of decomposition go up. So the slower, warmer water has higher rates of decomposition, and decomposition puts both methane and carbon dioxide, which are both greenhouse gases, into the environment, into the atmosphere. All right, I told you I was going to show you a picture of a levee. This is a levee along the Mississippi River. This is the river. All right, and there's a bus going down. So here's this is the road that goes along the levee, and you can see that there's a house right here, right? There's a farmhouse. So all of this land that's right here is floodplain. So this is area that's been enriched by the periodic flooding of the Mississippi. Now that land is no longer receiving periodic floodwaters unless the water goes over the levee. And there is evidence right here that the water has gone over the levee. Levees mitigate flooding, but they don't completely prevent it, because if you look right here, there's some floodwaters sitting there on that lower left-hand side of your screen. So the Mississippi had overflowed at some point, and you got some residual floodwaters here. But if the levee wasn't here, I want you to kind of picture what that would look like. The house and that farmland would be in the floodplain. Now the house would be subject to obviously periodic probably damage due to floods, and this land, what we would call river bottom land, is probably very fertile from before the levee was built, when the river was allowed to actually flow through there. All right, this is a picture of a dike in the Netherlands. It's built to keep the sea from flooding the farmland. Here's the sea, here's the farmland. Okay, and the farmland is actually below sea level. So we have to keep, this dike is designed to keep the ocean from flowing in there. Now, dikes are usually used in conjunction with pumps. And you can see right here, there's some wind turbines in the back. Now, it's unclear in this picture if the wind turbines are used to generate electricity, because there are lots of wind turbines that generate electricity off the coast of Northern Europe, or if they're being used like the traditional windmills were used to drive pumps that would take this water out. Again, a lot of the pumps are now run by electricity, but one way to generate electricity is through wind power. But there are wind turbines in the background here. Whether those are creating electricity for to go directly into the electrical grid or running pumps is unclear. All right, so here is a picture of a very, very large hydroelectric dam. This one is in south central Russia. This is the Sayano-Shushkinskaya Dam. Not that you need to remember that, but Russia has lots and lots of hydroelectric dams. And this was a very large river. This is the river outflow. And this is the reservoir that's behind. That's where the river has been dammed and is backing up into a reservoir behind that dam. What you're seeing here, the turbines would be right about here. The water flows in through intakes at the top of the dam. It spins the turbines, which are located inside the dam, and then the water flows out. You can see the water kind of coming down this area right here, flows out down the backside of the dam, and then goes down into the outlet of the river. Fish ladders. So one of the things that we talked about with dams is that they impede fish migration. Several species of fish migrate each year, and they migrate upriver back to where they were born. Salmon in particular are a species that do this. Well, if you have a dam in the way, fish are like, yeah, what am I going to do? So we have to help them get from the river that they're trying to swim up past the dam. So how do we do that? We do it with a fish ladder. There it is right there. This particular fish ladder that you're seeing in the actual photograph is on the Klamath River in Oregon, which I got to visit this past summer, and it was super exciting. So this is what the fish would do. They would come up this way, and then they would turn in what they call a turning pool, and you can see it in the diagram actually right here. Down at the far end of that picture is the turning pool, and then they continue their journey up this way, right? And then they're at the top of the dam, and then they fly over the top of the dam and land in the reservoir, swim across the reservoir, and continue their way on through their migration. And I wanted to show you a diagram, which is down here, of how a fish ladder works. So the flow from the ladder attracts the migrating salmon. They come in down the bottom. They jump. Oh, by the way, this is how salmon migrate. Actually, they actually jump. So these jumps are not like stressing them out. That's how they normally move upstream anyway. Jump. Here's your turning pool. Jump, 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 and they're at the level of the dam. And then they go on their happy fish way, and they can continue their migration. There was an FRQ on salmon migration routes and fish ladders and fish mortality on dams in last year's AP exam. I graded it. Okay, sometimes we need to move water from place to place. The way that we do this is through aqueducts. We can also do it through pipelines, but it's primarily done through something called an aqueduct, not aqueduct, but aqueduct. They're canals that move water from one location to another. You might associate aqueducts with like the ancient Roman Empire, but we still use them today. In fact, two of our biggest cities in the United States, New York and Los Angeles, rely on big aqueducts to get much of their water. In New York, the Catskills Aqueduct brings water from the lakes and streams of the Catskills Mountains over 120 miles into the city of New York. And in Los Angeles, which is a very dry city natively, by the way, the Colorado River Aqueduct brings water from the Colorado River 250 miles across the Mojave Desert into Los Angeles. Los Angeles actually, Angelinos are subject to water restrictions quite a bit because if the flow of the Colorado was low that year from like lack of snowmelt or whatever, Los Angeles doesn't get all the water that they need. And it's a very water hungry city. So they practice a good bit of water conservation over there. Aqueducts, again, are famously associated with the Roman Empire, and many Roman aqueducts still stand today. I will show you a picture of one. Great. This is a Roman aqueduct. This is a famous picture. It's the arches of the Pont du Gard in Roman Gaul, which is in southern France. The actual aqueduct is right here in this top tier. Okay. That is a kind of an open canal that carried water to the city of Nîmes during Roman times. The lower tier that's down here was expanded to carry a wide road across the river. And, you know, people are like, oh yeah, the wide road's modern. Yeah, so modern. It happened in the 1740s. But the Roman aqueduct was already there. The city put the lower tiers on in the 1740s so they could have a bridge across the river. All right, so one additional way that we can make fresh water out of salt water is a process called desalination. It's also sometimes called desalinization. It is exactly the same thing. It is a process where we basically take brine water, most often ocean water, take the salt out of it, and then use the fresh water. Desal is used primarily in water poor countries of the Middle East. The Middle East, as you might imagine, is a very dry area, and they do not have access to a lot of fresh water. So desalination makes sense in this context. There are two common desal techniques. The first is distillation. That is basically boiling of salt water to create steam. The steam is captured and condensed and then used as fresh water. That's a very straightforward way, right? Because the salts and the impurities are left behind and you get basically distilled water. The other way to do it is as a process called reverse osmosis. The salt water is forced under high pressure through a semi-permeable membrane. Pure water can cross, but the salt can't. So you get water on one side and salt and other impurities on the other. Desalination has several drawbacks. The first and the major drawback is it's incredibly energy intensive. It uses a lot of electricity to do either distillation, because you have to boil the water, so there has to be an energy input there, or to generate the pressure needed for reverse osmosis, which is also an electrical process. So I want you to think about the Middle East. The thing that they have lots of is energy. The thing that they don't have lots of is water. So again, doing desal in the Middle East makes sense because they have sources of energy and they can generate lots of electricity. They just can't, they have to get water from somewhere. So again, it makes sense. The dried salts that are left behind from either distillation or the brine, which is the concentrated salty liquid that's left behind during reverse osmosis, they have to be disposed of. And they're categorized as hazardous waste. They can't be disposed on land because if you dispose of them on land, you're going to contaminate your soil. You're going to salinate your soil. If you dispose of them in a bay or an estuary, which would be a part of the ocean that's like kind of nearby to human habitation, you can really harm aquatic life because this salt is really, really concentrated and there's a lot of it. When they do desal, they're not doing it like 1 barrel a day. They're doing millions of barrels a day. And so there's a lot of salt. So what they normally do is the salts are normally disposed way out in the open ocean. But again, is that causing harm? Probably. We are not exactly sure how much. So here is a map, which I liked. It's predicted water availability per capita by the year 2025. And so it's a projection. The projection is based on World Bank predictions. So as you can see, look at the key down here. We have a couple of countries with no data, but the dark blue areas are areas of surplus. And as we move toward red, we move towards scarcity and extreme scarcity. Some of the things that you probably want to note here is that some of the areas that are in scarcity, stress, and extreme scarcity are areas that are politically unstable to begin with. We are going to be talking a lot more about this because access to fresh water is actually a major political point and can cause open warfare, and already has. We're talking about like the world's, we got the U.S. here and most of the world here on the fringes. We have access to water. We don't have to worry too much about water. But in these water hungry areas, Northern Africa, the Middle East, on through India, Nepal, Pakistan, China, we're gonna see some destabilization politically due to water issues. Okay, so let's talk about water footprint. You may have heard the term carbon footprint. We're going to talk about water footprint. The U.S. global water footprint is among the world's highest. In fact, it's generally, we vary between us, Australia, and Spain. And I'm not sure why Spain, but we use an awful lot of water. When we look right here, this is gallons per capita per year. So take a look at that number. 655,939 gallons of water per person. That's what per capita means. Capita means head. That means per person. Per capita per year. That's a dang lot of water. All right, so again, here's our global average up here at the top, right? So we are well above the global average. The definition of water footprint is the water footprint of a nation is its total daily per capita use of fresh water. The U.S. yearly water footprint, like we just pointed out, is among the world's highest. It's nearly 700,000 gallons per person per year. That comes out to about 2,000 gallons per capita per day. And obviously, not all of us are using that amount. We're just not. I can guarantee you I'm not using that amount. But this takes into account all water use. Okay, so all water use in the nation divided by the number of people that are in the nation, and we just use a lot of water. The single largest use of water worldwide is for agriculture. The single largest use of water worldwide is for agriculture. That is often a test question. Raising livestock takes huge quantities of water. We lump livestock in with agriculture. So when we talk about the use of water, right, we've got agriculture, we've got residential, and we've got industrial use. And the largest worldwide use of water is for agriculture. However, country by country, these three components, what's the biggest component, changes. Part of industry, actually, and I'm going to say this because this has often been, I've had people ask me this when I train teachers. Industry has the largest withdrawals of water worldwide, but in industry, a lot of the water that they use, they reuse. They filter it and use it for another industrial process. But that is not the case in agriculture. In agriculture, they withdraw a lot of water, and that water is either consumed by livestock or put on plants, put on crops for crop growth. It cannot be reused again. So there's no way to take that water back and to recycle it. So agriculture uses the most water, even though industry might have the greatest withdrawals of water. And that is a sticking point all the time. And I have to kind of explain that to APES teachers. Since it is the world's greatest consumer of fresh water, agriculture also has a huge potential for water conservation. So when we're talking about ways to conserve water, let's focus on agriculture because they use the most. So let's talk about how crops are irrigated. Remember, in subsistence agriculture, we're largely just relying on rains and when the rains come. And if the rains don't come, we have a drought and the crops fail. But in industrial agriculture or non-subsistence agriculture, we irrigate. How do we do it? The first way is furrow irrigation. Furrow irrigation is the oldest way to do that. So you have crops in rows. In between those rows, you have furrows or little like mini valleys. You just flood the mini valleys with water, and the water seeps into the ground and waters the roots of the plants. Furrow irrigation is about 65% efficient. 35% of that water either runs off out of the field or evaporates before it can actually get to the roots of the plants. Flood irrigation. Flood irrigation is mainly done in places in Southeast Asia when they're doing rice cropping. The entire field is flooded with water evenly. Flood irrigation is disruptive to plant growth, but it is also up to 80% efficient. It ranges between 70 to 80%, so up to 80% efficient. So it is more efficient than furrow irrigation. Flood irrigation can really only be done with certain crops because it is disruptive to plant growth. Spray irrigation, which is also called center pivot irrigation. This is the one that most of the world's industrial agricultural systems use. Water is pumped from underground. So you have an underground aquifer, and there is a pipe that goes into this underground aquifer, and it is the water sprayed across a field from a nozzle that looks like a giant lawn sprinkler. Spray irrigation can be very efficient, up to 95% efficient, depending on the types of nozzles used. There's two different types. One is a center pivot where you've got like looks like a giant lawn sprinkler, and it is literally just spraying water through the air onto the crops. Another way is to use these long pipes that have nozzles that hang down on short hoses. That actually makes the process a lot more efficient. If you're spraying the water from a central pivot in like a giant lawn sprinkler, a lot of that water is evaporating before it even gets to the plant. But if you are taking the water via a pipe and spraying it with these little mini nozzles that hang down closer to the plants, then not as much is evaporating. And so it's a much more efficient process. Those pictures are actually in your textbook and you can look at them as well. Spray irrigation is expensive because you have to tap into groundwater resources, and you have to have machinery to do it. And it can lead to salinization of the soil. Any time you're using groundwater for irrigation, groundwater has dissolved salts in it. So the longer you irrigate with groundwater and pumping it through the air where it's prone to evaporation, the more salts you're going to get on your crops. Drip irrigation is our fourth irrigation technique. It is the most efficient method. It's at least 95% efficient. It can be very, very efficient. It uses a slow dripping hose to deliver small amounts of water directly to the roots of the plants. There was a picture in one of our previous presentations, but basically the pipe or the hose lays on the ground next to the row of plants, and it just basically drips water out of it. The water goes directly into the soil, directly to the roots of plants. So there's very, very little evaporation. This method also discourages weed growth because the surface in between the rows of your crops, the surface of the soil remains dry, and so weeds don't have a source of moisture to grow in. So hydroponic agriculture is the cultivation of crops in greenhouses with their roots in a nutrient-rich solution, like a watery solution, but no soil. So it's soilless agriculture. Sometimes there's a little soil, but most of the time there's not. The water is uptaken by the water that's not uptaken by the plants is reused. So you have these plants and their roots are hanging in the solution, and the solution flows by their roots and flows out the other end of the pipe. So that if the water is not uptaken by the plant, the water is just reused, filtered and reused. So the method uses up to 95% less water than soil-based agriculture. The other thing is that since hydroponic crops are grown indoors, little or no pesticides are needed because you can basically just keep the pests out. So here is a very futuristic looking picture of lettuces being grown hydroponically. So these white structures that you see right here, they're just big long tubes, and in the tube, you can kind of sort of see it on this side, there is an open, a little gap where each one of these lettuce plants is planted. They put basically a seed plug in there. It's got the lettuce seeds in there. They stick it in there, and that plug remains saturated with the nutrient solution. The nutrient solution you can see is actually being piped in right here. There's the pipe. So it's being piped in, and it flows down the rows of lettuces, and at this end way over here, whatever is not taken up by the plant roots is pumped out of the pipe. So there's a flow. It's pumped out of the pipe, filtered, and sent back through the rows. So there's no soil being used here. It's all grown indoors. Obviously, pesticides don't need to be used because you can just shut the doors. This is a greenhouse. You can see that these plants are protected from the weather by the glass ceiling here. The sunlight can be let in, but nothing else can. As I had said before, industry also uses large amounts of fresh water. Industrial water uses include generating electricity, which is 50% of all water used in the United States, cooling machinery, refining metals and paper, and by the hydraulic fracturing process. And usually, again, this is usually the frackers actually buy water rights from somebody who has the rights to it, oftentimes agricultural interests. Again, as I mentioned, agricultural water use, industrial water use, although industry has higher withdrawals than agriculture, The reason it's not the largest user is because a lot of the water that they withdraw, they reuse. Household use accounts for about 10% of water use in the United States. So although it's important for us to conserve water domestically in our houses, it's only about 10% of water use in the United States is actually done in our houses. Each American uses an average of 157 gallons of water each day. Indoor water use across the United States is essentially the same. However, outdoor water use varies widely by region. The single greatest use of domestic indoor water is toilet flushing. Yes, most of the water that we use indoors is to flush the potty. Now, this outdoor water use right here, drier regions, more arid regions use a lot more water than more temperate regions. California actually has of all the states in the union, California has the highest outdoor water use, and you can see why. It's an arid state, and when people want to grow something outdoors, they have to water it. It's not an option. I just wanted to clarify right here, each American uses an average of 157 gallons of water each day. Now that's a lot less than the 2,000 that we saw on the other screen. Remember, when we're talking about water footprint, that 2,000 per capita is all water use. All water use. That's industrial, agricultural. That's total water use divided by the population of the country. And you can do that by year or by day. So when we're talking about U.S. total water use by the population, it's about 2,000 gallons a day. When we're talking about domestic use, right? Domestically, to flush the toilet, get a drink of water, take a shower, we're talking about 157 gallons of water. So don't confuse those two numbers. Access to clean water is actually a human rights issue. It's a social justice issue. Nearly 1 billion people, that's 15% of the world's population, 1 billion people worldwide, lack access to clean drinking water. They just don't have it. Every year, nearly 2 million people die of diarrheal diseases related to drinking contaminated water. 90% of those are deaths of children aged 5 and younger. I have seen this firsthand because I used to live in China. I'm telling you, it's very, very, very hard for me to process. This is a child, right, in China. This is Fuyuan County in China. This is mid-latitude China, so not northern China or southern China, kind of middle of the country China. This is the stream that she's drinking out of. Take a look at that stream. That's what she's drinking out of. It has not been filtered. She just literally took the family's cooking pot, went over there, got some water out of that stream to drink. That is not uncommon. And I actually chose this picture. Some of the pictures that you see of children in Africa drinking out of open water sources are so, they're beyond imagination, because what they're drinking out of water sources that literally, it's a mud puddle. They're drinking out of mud puddles, and that is the only source of water that they have. So when we're talking about it being a human rights thing and it, access to fresh water being a real big problem, it's a huge problem. Imagine that. Just put that in your mind. And we're gonna investigate this more in class, but it's a big deal. And 90% of those 2 million deaths are children aged 5 and younger, because this is what they're drinking. This is what their water source looks like. So water is an essential resource for human life. You can't live without it. You can't live hardly any time at all without it. But who owns water? Who actually owns water? The issues of water rights and water ownership have created conflicts worldwide. In water-scarce areas like India, Nepal, and in the Middle East, water conflicts have contributed to political tensions for years. And I think your textbook talks about the Arab-Israeli War in 1967. But, people in the Middle East have been fighting over water for centuries. on a smaller scale. Who owns this oasis? Do you have the rights to get water from this well? It's a big deal. As fresh water becomes even more scarce due to global climate change and increasing water pollution, conflicts over water are going to increase. They're going to continue to increase. And I want you to think about that map that you just saw. Where is the scarcity going to come? It's coming in regions that are already political powder kegs. So it's going to lead to possible violence and political destabilization of entire regions. Are we prepared to deal with that? Water conservation is, especially in first world countries, is pretty important. Although water cycles on the planet, you guys, we know about the hydrologic cycle, and we'll talk more about it as we go through the course. Although it cycles, there's ultimately a finite amount of fresh water that is available to us. And again, the amount that's available to us is changing due to global climate change and increasing water pollution. Water conservation is essential to maximizing our supply of available water into the 21st century. So how domestically can we conserve water? Now remember, domestically it's about 10% of the water that we use each year. And so it's not the largest amount of water, but conservation makes a difference, and it's something that we individually can each do. So you can install low flow shower heads and toilets. You can install a dual flush toilet. You may have seen these in restaurants or in airports. A dual flush toilet has a handle that goes up for more water and down for less water. Sometimes they're backwards of that. But they have a liquid waste setting and a solid waste setting. So they use less water to flush liquid waste than they do for solid waste. You can switch to a composting or an incineration toilet. And while these are often used in places where water is inaccessible or it's a very arid climate, they can be done in a household. A composting toilet is a toilet that's got basically some fibers and pine shavings down there, and the waste is composted. There's very little odor. It's composted into a rich soil once a year. A company comes and removes the cartridge at the bottom of it. It's basically it's been turned into soil. They sterilize the soil under high heat, and you have soil that you can use in your garden. An incinerating toilet sounds a little scary, but what it is, it basically flash heats the waste to about 2,000 degrees and burns it all up. There's very little odor, and it basically does it when it gets to a certain point in this tank, and then the tank, you hit this incineration button and it heats up the tank and basically vaporizes all of the waste to ash. And again, the ash is taken out about once a year, and the ash is actually very nutrient rich. You can use it on your garden. You can upgrade to reduced flow washing machines and reduced flow dishwashers. Most of the new appliances that they sell now are water and energy efficient. If you live in an older house, upgrading is a good idea. You can xeriscape your lawn with native plants instead of grass. Plants that are adapted to the climate in which we live is a good idea. Xeriscaping basically just means that that you're using plants that are adapted to your native climate. So whereas you're used to seeing lawns with a grass in front, grass is actually pretty water hungry. And a lot of areas that are arid, grass is not a good choice because it has to be watered daily. So if you plant plants that are native to the area, they don't need as much water. Another way that you can conserve water is by using a rain barrel. You can collect precipitation, and that precipitation can then be used to water your lawn. Municipalities are looking for larger scale ways to conserve water as well. So the ways on the previous slide, we're talking about domestically, individual households. How can we conserve water? Some cities are using the surfaces of rooftops, which are impenetrable, they're impervious to water, as potential precipitation collecting areas, kind of like a huge rain barrel system. If you could harness the water that falls on those rooftops and then use it for municipal use, that would be a wonderful way to conserve water. Also, if city regulations permit, some homeowners are having professional plumbers divert their household gray water. So what's gray water? Gray water is wastewater from bathtubs, showers, and bathroom sinks and washing machines. So is it clean enough to drink? No. Does it have bacteria in it? Yes. But is it polluted like to where you couldn't put it on your lawn? No, it's not. So we're taking this wastewater from baths, showers, bathroom sinks, and washing machines, putting it into a collection unit. It's being filtered before you put it in there. Now, not chemically filtered, but mechanically filtered, where they're taking out like the lint from the washing machine and stuff like that. And that water can be used to water your lawn, to wash your car, or to flush your toilet. If you've ever been to the Perot Museum, which is in downtown Dallas, the Perot Museum of Nature and Science, they use gray water to flush their toilets. The water is actually bright blue because they put a disinfectant in the water, but it is reclaimed wastewater from the sinks that they're using to flush the toilets. Contaminated water is, or it's also called black water, is wastewater from toilets, from kitchen sinks, and from dishwashers. Black water cannot be reused. It has to be disposed of as sewage. Obviously, you're not reusing toilet water. Ugh. But again, so if it's coming from a toilet, a kitchen sink, or a dishwasher, it can't be reused. If it's coming from a bathtub, a shower, a bathroom sink, or a washing machine, it can be mechanically filtered and used to do other things with, if city regulations permit. And in the U.S., a lot of times they don't.